My name is Michael van Schoor. I'm from the CSIR mining cluster, and I'm going to tell you about the in-mine electrical resistance tomography trial surveys that form part of the Advanced Orebody Knowledge Work Package 4.2 in the past year. I'll start with a problem statement. So basically there are two major pain points in the deep level mining industry in South Africa. The first one is that of optimal extraction, which basically means that when you mine a block, you try to take out as much of the ore body with as little dilution as possible. The second pain point is that of the zero harm objective. So we know that over the past couple of decades, the fatalities in the mining industry have steadily been on the decline. However, the trend is now plateauing, and we're still losing a lot of people every year, especially through falls of ground, which is associated with poor ground conditions. And often these poor ground conditions are associated with disruptive geological structures. So in a nutshell, the key to achieving the zero harm objective and optimal extraction begins with a good understanding of the ore body and any geological features that might be disruptive that lie ahead of the mining phase. The solution that we propose is that of in-mine geophysics to gain that information about the ore body ahead of mining. One of the proposed solutions is a method called electrical resistance tomography, or ERT. The method is basically based on the medical equivalent of electrical impedance tomography, where sorry, can I start the slide? One of the proposed geophysical methods is that of electrical resistance tomography, or ERT, which is based on the medical equivalent of electrical impedance tomography, where electrodes are placed around a target body and the internal structure of that body can be mapped. We do the same, but instead of using a human target body, we use the earth. So in the mining context, that body would be an unmined block between two raise lines, for example. And we place our electrodes around that body in the raise tunnels and any other on-reef developments or boreholes that might be available. Okay, so there's a second part to the problem statement. We tried to introduce the ERT method to the mining industry more than a decade ago. And even though it was recognized that ERT was the ideal reconnaissance tool and that it could delineate geological structures up to 100+ meters ahead of mining, there were a number of key disadvantages that caused the method to basically be mothballed at the time. These disadvantages include the fact that it was logistically challenging to apply, it was very time consuming, and also the integration of the outputs with mine software and mining models was not optimized. And there was also general perception that the outputs of the ERT was not very useful in that form to the end user. So the R&D approach that we adopted in this project included the following activities. We investigated and assessed the technological advances that have been made in recent years that might now make ERT a viable or feasible in-mine tool. We tried to quantify the improvements in ERT performance, especially on the logistical side. And we investigated the incorporation of ERT outputs into geological or even risk models. And the whole project centered around a couple of demonstration or trial surveys. I'll present one of those case studies in this presentation today. So if you look at a schematic of our test site, you can see that our target body is there in the center of that circle. It's a pillar in a mechanized section, fairly small pillar. On the right, you can see the target feature that we were focusing on was a geological fault that runs through the neck of that pillar. And the idea was now to place 30-odd resistivity electrodes around the pillar to see if we can map the internal structure of that pillar, and obviously the impact of that fault line that runs through the pillar. Here's some pictures of our survey underground. It shows how we prepare the electrode sites by drilling holes, placing anchor bolts into those holes, connecting all the electrodes up to the resistivity meter using multi-core cable, and then running the data acquisition from that yellow box, which is the resistivity meter. We were able to show that if you compare the total time requirement of a typical ERT survey, we've been able to cut down that requirement to almost 50% of the time it traditionally took to conduct ERT surveys underground, which now makes it quite possible to conduct a ERT survey in a single shift. We also showed that with proper georeferencing, it's possible to take the ERT output and incorporate it with the mine plans. In this slide that you see, we actually used the LiDAR method to create a point cloud of the mining environment to use as georeferencing and to transform the ERT coordinates to the absolute coordinates used by the mine. You can also see on that image that we very clearly were able to map that fault line that runs through the pillar. In conclusion, we've shown that in-mine ERT provides the ideal medium-term planning reconnaissance tool for detecting and delineating disruptive geological features ahead of mining. We've shown that the technological advances in recent times have improved significantly enough to enable single-shift routine surveys. And we've also shown that ERT outputs can be incorporated into mine planning or other 3D visualization software platforms, provided proper georeferencing is done. Thank you.